halfway through the class. I mean in the following sense, which is that there are 12 sessions, I think, total, and 2 of those will be project presentations by you guys, so which means that 10 is our share of the course, and this is the 5th session. So at the end of this session, we will have finished half the course. So last time, what Anand covered was essentially using simple methods of averaging to give you insights, right? Before we sort of take off from there, and Anand and my division of responsibilities is broadly, I'm covering the theory and he's covering the practice, right? The reason why averages are important is because the claim of all statistics, I mean, statistics would be useless if you couldn't summarize the world using statistics. I mean, if you had to memorize every single piece of data, then you have no reason to do statistics, right? So statistics, actually the rationale for using statistics is that the world can be compressed into something smaller than what it appears to you when you collect the data. But there is of course the issue of why is it at all that the world is compressible? Maybe it won't be. Right? So if I just gave you a random sequence, and an example of a random sequence would be just doing a coin toss, you can't summarize a coin toss. Right? Of course, the only thing you can summarize there is the probability of, say, heads or tails. And what the idea of probability already is telling you is that some kind of summarization is possible. Right? The whole point, after all, behind statistics, probability, all of these is to predict the future, reduce uncertainty, take insurance against unforeseen events, so on and so forth, right? And all of that depends on the future being, or elements that you have not observed being somehow predictable on the basis of stuff that you have observed. And that usually depends on the existence of a summary. And that's I mean, you might think that that's the most trivial kind of observation, right? That of course, if statistics were not possible, then you can't summarize, right? So if I just gave you a sequence of elements that did not have any logic to it, there's no summary there. So average, by the way, as a number, if you're just taking a bunch of numbers and you divide by the n, where n is the size, really doesn't mean much if the set of numbers wasn't summarizable, right? So if they were all over the place, the average doesn't have any meaning at all. Similarly, for any other summary statistic you might want, whether it's a median, mode, standard deviation, all of those are dependent on the summary actually being representative of the sample and predictive of other members of the statistical data that you are drawing. Now that is what this session is about, which is basically why is it that the world seems to be capturable in very small numbers. Okay? So I'm going to start with something that you probably did not think of when you signed up for this course. Do you know what this is?
Dumb people.
Dumb people know. Huh? Tick. Who said tick? Ah, he knows the answer. He's seen the book from which it came from. The tick, incidentally, this is in India we don't have too many ticks, I think. But in definitely North America and in Europe we have tons of ticks, and they suck your blood and they grow larger and larger after they suck your blood. They also sometimes carry something called Lyme disease, which is a very debilitating illness. But what's really interesting about the tick is that it senses something very, very simple. It essentially has a three-dimensional sensor array, and it says that it only, so So things that meet that, and they are all temperature driven, trigger this response in the tick. So it senses the temperature changes in the environment under it, and once the temperature reaches a certain threshold, it will jump, into the air, hoping to land on food. Okay. So what the tick really tells us, therefore, as far as the tick's world goes, that's all there is. It's just these three different, essentially it's something that says food is there or not. Okay? So the entire world is reduced by the tick to these very few dimensions. And what's interesting is that since they're still alive and thriving, that seems to be enough, right? So as far as the tick goes, if you compress the entire universe into these two dimensions, that's more than enough for it to survive. Right? So that's the quote from a very famous book by Estonian-German biologist Jacob von Oesterreich. Right? So it says that a fine sense of temperature betrays this to her. She has reached her prey, the warm-blooded creature. It only remains for her to find a hairless spot. There she burrows deep into the skin of her prey and slowly pumps herself full of warm blood. Experiments with artificial membranes and fluids other than blood has proved that the tick lacks all sense of taste. Once the membrane is perforated, she will drink any fluid of the right temperature. So as far as the tick therefore goes, it first detects that, or according to it, that something interesting might be passing by, jumps, digs, starts drinking as long as the blood is of, or whatever that fluid is of a certain temperature, right? So this extremely low dimensional representation of the world is more or less enough for the tick. Okay? Now what's really interesting, and this is why the connection to this course and what thinking data, it's not as if the world itself is three-dimensional, right? I mean, there are many, many, many different things that could potentially be measured by the tick. It could measure motion, it could measure sound, it could measure the texture, right? Because skins have a particular texture, when animals move, they make a certain sound, and obviously if they're moving, they're also having a characteristic pattern of motion. So those are the things that in principle, and many, many others that the tick could be using, but it's only using these three, right? And these, we don't know exactly why it's using these three. There could be some kind of evolutionary arguments made as to that this makes survival easier for the tick. But the fact of the matter is, it's these three and no others, and that's the real question, right? Which is that why is it that the tick or the statistician is measuring those properties and not others? Once you measure a property, then you can take averages, you can take standard deviations, do all those things. But until you know what to measure, you don't even have a chart with the scales written, right? And why I'm saying that is a great deal of what you learn typically in statistics or data science type classes is what are the functions or the numbers to run on a given data set. But actually the hardest question is what measurements to do in order to get the data set in the first place. And if you don't know where to do that or how to do that, so to give you an example, right? Suppose that I want to do mortality statistics. So I want to find out how long people are going to live. Now you could do that on the basis of age. You could also do that on the basis of other variables. So you could, for example, do that on the basis of social class, right? You could, in fact, do it in a way that takes both into account. But obviously, the mortality rates for chain-smoking men are very different from the mortality rates for, let's say, completely teetotaling women, right? Upper class women, let's say. Okay? So if you clubbed all of them into the same category, you simply would not be able to get anything meaningful out of it. Your answers are not that interesting, right? And so this is the problem that any statistician faces, which is what are the dimensions in which you want to array the data in the first place. The law of small numbers basically says that of all the things that could matter, only a very few do. Right? That somehow, of the zillions of things that one could potentially monitor, only a few actually are relevant to any question that you want to answer. Okay? So if you want to find out if the sun goes around the earth or the earth goes around the sun, it really doesn't make any sense to find out if it is winter or summer or whether the wind is blowing hard or soft or any of those things. All of that can be idealized away, right? And this is in fact the basis of science, right? Science would simply be impossible if you had to take every single thing into account. So underlying any kind of systematic inquiry is this idea that of the various things that could matter, only a few do. Right? And this is a very, very abstract general principle, but if you keep this in mind, you'll probably come up with better hypotheses than if you just randomly started doing things. I mean, there's a danger in this age of big data that you just throw whatever you want against the data and then you hope that some kind of insight will just emerge out of it. I mean, that's possible, but almost invariably, you have a hidden assumption about what matters and what doesn't. It's impossible. I mean, this is, however one does it, it's impossible to derive structure from lack of structure. Okay. And therefore, if there is structure in the data, it will be either because the world's made that way, so the sun, the earth goes around the sun, and not the sun going around the earth, or because perhaps our minds are made that way, meaning that we are too stupid and therefore we can't really understand a world of zillions of variables, and therefore whatever the world really might be like, in order for it to make sense to you, it has to be reduced to a manageable package. Either way, it doesn't matter, right? Because whether it's our incapacity to understand the world or the world's great willingness to present itself to us in an easy way, the law of small numbers holds. Right? So let's just explore this a little bit. That maybe our minds are made that way. Maybe our minds are such that you can't really grasp the too complex a world, and so you have to simplify it. This is actually not a bad assumption. Right? I mean, whether human beings in general are made that way or not, most of us work or communicate with people who can't necessarily understand the complexities of every single analysis that you're doing, right? And so, whether it's your boss or your employee, or whether it is a client or somebody you're telling a story to, you want to make sure that you tell a simple but effective story. Okay? So if our minds are indeed made that way, what happens? So, sorry for those people who have seen this graph before. Do you know who these people are?
Philosophers.
Right? So this is actually a subset of a very interesting network that was drawn by just taking a look at with all the philosophers in Wikipedia and trying to find out who's linked to whom, right? So if the page of philosopher A cites philosopher B, then you have a link. Now you can see who the big numbers are here. Aristotle is obviously the biggest. Plato is slightly smaller, for people like Descartes, Leibniz, right? There are some strange people in this, like Leo Strauss, who is not a very famous philosopher, but as it so happened was a very influential interpreter of Aristotle and Plato in Chicago in the 60s, 70s. right? He greatly influenced Paul Wolfowitz, and therefore partly led to the Iraq War. So if you think about it that way, he is an influential philosopher in that sense. Okay. And people like Eric Fogelin, again, these are all very unknown people. So what this map therefore tells you, supposedly, so this is the raw data, supposedly, right? That you are trying to figure out who's an influential philosopher by looking at this. And you might say, oh, Aristotle is very influential, Plato maybe not so. But you might actually think that Leo Strauss and René Descartes are about the same level of influence, which is, of course, not true at all. Right? So that's really the problem, which is that in this representation, which is again very low dimensional, right? If you think about it, it's a one-dimensional representation, maybe two depending on how you think of area, of who is influential. The larger the circle, the more influential you are, and therefore you are reducing a very complex historical process of which philosopher did what and who influenced whom to a one-dimensional representation. Let's take a slightly different one-dimensional representation. This is only, by the way, of the ancient Greek philosophers. So you have Socrates on top, you have Aristotle there, Plato underneath. You can see that, incidentally, the previous one does not have Socrates. That's sort of strange when you think about it. But there's a very good reason. It's that Socrates didn't write anything, right? Plato wrote everything that we know about Socrates. So as a citation, it's always going to be Plato. So that's a slightly spurious thing, which also makes you think that Plato himself is sort of overinflated here, right? Because it includes both Socrates and Plato. So it's stuff that you might attribute directly to Plato and stuff that you might attribute to Socrates through the mouth of Plato. But Socrates is, in this diagram, much more clearly represented as an influential person. Right? So you have Socrates, whose student was Plato, whose student was Aristotle. Aristotle's great commentator was Theophrastus, and then you have other people like Zeno of Alexandria, Epicurus. So this is really the top 20 hits of ancient Greek philosophy. And that's what you really want to get out in some sense. Of course, a data-driven approach will suggest that the unknown philosophers, the zillions of students of Plato's students, and so on and so forth, also probably actually contributed to this tradition. But they are completely absent here. Right? And therefore, this sort of chart negates the influence of all the soldiers in the army. It only gives you the generals. Right? So that's the negative side of a completely schematized diagram of this kind. So how do you get the insights here, which are showing how Socrates influences Plato, who influences other people very directly, but then combine that with the data-driven approach in the previous diagram, which is showing you all the kinds of connections. Of course, this is from Wikipedia. A much better diagram could be gotten if we, so once work in the digital humanities gets better and better, and we have all the corpora of texts from the 2nd century BC and so on, you can see the cross-references in them directly. So you wouldn't have Leo Strauss anymore, right? So those kinds of mistakes would go away, and what you would have is a way to find out who influenced whom directly from the texts themselves. That's happening with Shakespeare, for example. Right? So Shakespeare can be studied now. So right now so most of our understanding of Shakespeare is this kind, right? Brilliant playwright, wrote all these plays. A lot of the things that we speak actually comes originally from Shakespeare, or that's what we think, right? Like, for example, I might say, I would be caught dead in a ditch with you. Well, that's Shakespeare. Okay. So in that sort of top 20 hits, Shakespeare is the biggest hit of all time. people have done these studies, people have done these studies of Shakespeare's texts, cross-compared with all the texts. The great thing Google Books has done is to digitize all these texts. So you can now do a comparison of Shakespeare with all other playwrights who lived in his time, and you find out that, and not just playwrights, but all kinds of other published material, and it turns out that Shakespeare borrows a lot more than people thought he was doing. And that's not a bad thing. I mean, the whole idea of an artist is to steal, right? So Steve Jobs famously says, good artists borrow and great artists steal. So, most of Shakespeare's plays, after all, are based on other plays written in the past. If you are of a certain persuasion, you might say, actually, Shakespeare is from India or something. It's all in the Vedas. Okay. So does history writing create history? That's really the issue. Right? Because, see, history is a form of insight that we use routinely to learn about each other's lives. So if you really want to understand how some place was or is, reading a history book is better than, getting the GDP statistics, in my opinion. Anyway. So, but by eliminating, because again, if our minds are made in such a way that we are taking a very, very complex world and reducing it to 7 characters, there is always this danger that you're throwing out the baby with the bathwater. I don't know if that's Shakespeare. So if our minds cannot grasp these large numbers, we compress history into something very small, and there's a danger that you're actually missing out on some important influences. Right? That's the problem if our minds are made that way. But we can't do anything about it. Okay? The only thing you can do is to invent tools that will help you expand your minds, and presumably the big data tools that we're getting now. The second hypothesis is that our world is made that way. Which is to say that our world is actually simple. That's the founding principle behind physics. Right? I mean, if you remember your Newton's laws from whenever you learned them, the idea is these 3 simple laws pretty much generate all, at least, macroscopic phenomena. That's the claim. Right? So if that's the case, the world is simple, and so it's not surprising that it can be compressed to a few numbers. So let me give you an example of that. So if you look at and this is not in the natural world, right? So this is in the social world. If you look at the number of journals that have published papers that are the most cited papers, so you find out that there are lots of journals that seem to be publishing 1 or 2 highly cited journals, but it's clearly a very sharply negative slope, right? Because the number of journals that are doing very, very large number of citations. So for example, if you look at this one, it's about 22, 3 or 24 citations per paper for that journal. And that's an outlier, right? So you clearly see this negative slope. So in many, many situations, we find that you have this kind of hierarchical pyramidal structure, right? That the number of, so for example, the same thing, the number of people who, or if you look at the increase in wealth in the last 10 years, or maybe even the last 20 years, you'll find out that the top 1% had a much greater increase in wealth than the rest of the 99%. That's the famous 99% where it comes from. It turns out that the top 0.1% of the 1% does a lot better than the other 0.9% of that 1%, and so on and so forth. So in many, many situations, we find, therefore, that a few key nodes seem to be aggregating a great deal of the density of the network. Which is why, actually, if you go back to the Plato-Aristotle network, it becomes possible to, even in a data-driven kind of process, cut out a great deal. Right? Most of us don't have any citations, so we just don't exist as far as this is concerned. Right? And a very, very few people, so you can do this, you can go online and see who's being cited a lot, by the way. Most of them tend to be biologists. And that itself tells you something, right? It tells you about the relationship between citation frequency and the kind of academic discipline that you're in, and the number of papers you're publishing.
The diversity here refers to what kind of diversity of field? I mean, of
diversity of journals.
Yes,
so meaning that, so if you look at this axis, right?
Yeah.
It's by field, meaning that, but it's not by field itself. It is. So Nature could count as one journal,
Yeah.
and that would be for all fields. Science would be another journal. So these are. So I think it's a combination of the field that the journal is in, but also just of the journals themselves. So some journals clearly are aggregating more citations than others. Nature is a 32. Okay, so it's a composite index. It's not just number of journals, but I think it's some average over journal and fields.
No, so the next question is that then how come diversity, when if it is not just fields and if it's also the kind of journal it is, why is that an important sort of variable to look at when you're looking at citations?
So for example,
why diversity of journals? If the concept of diversity itself is
so here's the thing, right? Let's take just the sciences. You would want to find out which disciplines are doing, so if you're a university administrator, you want to find out, should I close down the maths department or not? Okay? And the way you might answer that question is to find out, how is my department, there are two kinds of questions that I can ask. How is my department doing vis-a-vis other maths departments on this citation index? I may also look at maths departments as a whole vis-a-vis other disciplines, and say maths is simply not getting enough citations, let's close it down. So that's the kind of reasoning for which you want the diversity index.
Okay, and not just the citation.
No, because you could argue that, look, we are getting 2 citations, but that's the norm in this field. And that would be okay if I was an individual mathematician comparing myself with.
Okay, yeah.
You can see the same thing in the global citations, right? So if you look at the percentage of total, so the US was 36.8%, and then in 1999, 2003, and 30.4% in 2004, 2008. It goes very rapidly down to China, right? 3.7%. So again, this is a winner-take-all system where objectively, so this is not made up, right? It's not because of the limitations of my mind. There is a pyramidal structure, and broadly speaking, only about 10 or so of the 200 odd countries matter. Okay, so you can neglect everybody else. Okay, what it means is that if you're doing a summary statistics, for most purposes, you can neglect, Vanuatu and actually most of India and lots of other countries. Okay. In fact, I wouldn't be surprised if within the US, so if you took the top 4 or 5 or 10 universities, they might form a huge chunk of that, right? So everywhere there is this sort of upwardly concentrated density of connections, which for those of you who are in the ecology group should be interesting, right? Because it might give you insights into how ecological systems work. Some of them may be flatter than others, but I bet you if you look at, let's say, biomass as one way of quantifying, all right? So biomass meaning if you take a given species and you look at the total weight of that species in its niche. So you take this IISc campus here and you see, if you take by species, you add the kilos or grams or tons that any given species has, you will find out which are the species that have the greatest biomass, right? And certainly in this campus, most likely it's going to be people. Okay. But in other parts of the world, it might be different. Insects are probably the greatest. Ants, I think, have a very high percentage of the biomass. Okay. So in all of these, therefore,
Can we, if you're talking also small numbers,
uh,
can we also, we could probably also see trends of tipping points, which are usually very small percentages, and that little shift.
so
can
that's
actually-
the interesting question. That's the interesting question, right? Again, if you look at the citation statistics here, but it's much more clear if you look at the next picture. Actually, I'll come to that later. The answer is that yes, ecosystems, companies, history, all of those change, right? So 1,000 years ago, India and China were by far the biggest contributors to the world GDP, if at all that made sense then. Now we are getting better than we used to be before, but say 50 years ago we were minuscule. Okay, so clearly there are winners and there are losers, but how that shift happens is a very interesting question. Again, our law of small numbers hypothesis would suggest that shifts always start small, but they have exponential rates of growth at some point. Right? For example, for the longest time, computers were mainframes, but then suddenly at some point, personal computing took over, and most of what was sold was a personal computer. I think now there's a shift, and I think that non-PC sales have finally overtaken PC sales now. So we are therefore, which is a way of finding out if a tipping point has been reached as far as the technology industry goes. Okay, so you can actually see the same thing. So that the world is made that way can be looked at even in this particular graph, which earlier I had illustrated as Socrates being important, and that somehow I compressed everything, or rather Randall Collins compressed a world's worth of historical data into this diagram. But what's clear in this particular version, just a blown up view of the previous one, the centrality of Socrates in just the personal connections, right? Who knew whom, makes him a very, very influential figure. Right? And that's objective. That's not something that is based on my impression of how the world works. Okay? So, what I'm trying to say is that this combination of the world being simple and mind being simple certainly is there in all these previous networks, right, which are all about human production. So whether it's companies, whether it is ideas, those are all stuff in the human world. It happens in the non-human world as well, right? So the Fortune 500 is an example of that. So take a look at the 2 out of 3 Fortune 500 companies are located in only 10 states. So again, there's a very sharp concentration of wealth, of just, I don't mean personal wealth, but in terms of company headquarters in a very, very few states. And of course, if you look at the global Fortune 500, whatever that would be, the US would gather a disproportionate number of those 500 as well, right? So again, there seems to be this concentration. So going back to what Dipankar was saying, creativity and influence are both graded, meaning that the origins of whether it is companies, ideas, species, typically tend to happen in small, dense networks. Okay? So it's not a surprise that Plato knew Aristotle, Plato taught Aristotle and Socrates taught Plato. Right? The easiest way to get a Nobel Prize is to study with a Nobel Prize winner. Now, whether that is because they have the pull to get you a Nobel Prize, or whether you are smart because you can worry about what the influences are, but the fact of the matter is that creativity starts out in small networks and influence narrows down the field with time. Meaning that the small number phenomena comes in two very different ways. One is any new thing starts out small. The second is that in the long run, all kinds of bottom-up influences can be normalized out. Right? So there might have been zillions of influences, but you can write a history as if only Shakespeare and Plato and people like that existed. I'm not saying that's right, but I'm saying that it is possible. Okay? Which is what the world pushes us towards small numbers, right? And network effects tend to dominate. So what's really interesting about networks and about large numbers in general, but especially network large numbers, is that despite these being very, very large networks, by the very fact of being large, they tend to become small. Right? So the 6 degrees of separation phenomenon that many of you might have heard of is possible only in large networks. If there were 6 billion people on Earth, but we were not really connected by Facebook and whatnot, we would be infinitely far away from each other. It's precisely the existence of large networks that connect large numbers of people in that case that makes the average distance small. So somehow the smallness is actually a function of the largeness of the network. Okay. And this kind of tuning, right, the fact that only a few things seem to matter, it's a very robust phenomenon. Right? I mean, you can play this in so many different ways. So for example, if the charge of the electron was even fractionally different from what it is right now, we wouldn't exist. Right? So all these numbers have to be exactly what they are for the world to be the way it is. And that's a common theme. Right? So whether you call it serendipity or intelligent design or whatever you want to call it, the fact remains that things can't be very different from, they tend to be, most things that can vary, nevertheless vary in very tightly constrained ways. Okay. Right? And the quick answer to that, why that happens is averaging, which we studied last time, that if you take any data and you summarize it, and you summarize it with various kinds of statistics, the whole idea is to compress lots and lots of numbers into one or two. Okay, and the answer seems to be that this is possible. And that's one of the great discoveries of mathematics, really, in the 18th and 19th centuries. Right? That somehow lots and lots of things put together behave as if they're all kind of just one thing. Okay? And that's what I'll call the law of large numbers. Right? Large numbers behave like small numbers. And there's a very precise way to answer that. But we'll take a break and then we'll come back and do that.